Hello everyone, I'm Aditya Mahajan of class 92 and we're going to start with a really interesting topic which I have thought of for the science week today, and it is the topic of does the future influence the past. Now, just in the background before we begin, I will be using the topic of quantum physics to settle this debate. Now, perhaps you may find quantum physics as a bit of a higher subject and you may find it as a bit difficult, but do not worry about that because I have taken all the necessary precautions to make sure to explain it in a language which would be understandable for you, which would help you get a grasp on the topic and on the question which we are trying to solve, and more importantly it would help you to like the subject more. So I've also thought it in a form of a thought experiment, which may be a bit different from the other experiments that you may see, because the experiments which we are used to are the practical experiments which we perform by hands, and then we go on to show something. However, this is entirely different. This is a thought experiment and it's quite of a unique subject as well. The question which we have with us today is, does the future influence the past? Now, we may be familiar to the opposite of the question, right? We may have thought about in our heads that if the thing I do today, it would affect the future, if it would affect my future, right? However, what if you could twist the question entirely? Does the future influence the past? Now, it may be a bit of a mind-boggling question, but don't worry, I'll explain it all to you. So let's proceed with the presentation. Imagine for me that we have three objects with us, actually three main things with us. We have a quasar. Now, a quasar, it's okay if you don't understand what basically a quasar is. A quasar is any celestial body. It has such a high energy. It emits a lot of energy, all right? It gives out so much energy and therefore it gives out so much light that it can illuminate a very wide expanse. So just take a quasar as a celestial mass which has a lot of energy. In a very vague and in a very layman language, you can discuss about a quasar in this form. And we do not need to go too far in a quasar. This is a normal galaxy. This is just any random galaxy. You can take it. And this is our planet Earth, right? Now imagine that the Earth is in its own galaxy, Milky Way galaxy. It's in that. Then there is some other galaxy, right? And then in some other place, which is quite far off, we have this quasar with us, right? Let me just wipe out all the ink here and let's explain it. Right. So imagine that the quasar emits a whole lot of light from it, coming from it, right? And it emits it from its starting point, and it takes a journey through here, passing through more than a billion light years, perhaps, because like the distance between all of this would be quite far off. And now a question might have emerged in your mind as to why I made the path of the quasar around this. And of course, there would be a second path of light, which may come around as this. Now, you might be thinking as to why I didn't just take the quasar's light path as this, because of course, mathematically, we know that the shortest distance between any 2 points would be a straight line. And any object would obviously follow the straight line, right? But why did the light coming from the quasar, being emitted from the quasar, follow such a weird pattern? Now, this is the topic of gravitational lensing, and it would be the second thing which I would explain in this presentation. So no need to worry on that. Let's just for now assume that the light follows such a path and comes to the Earth. Again, no need to worry on the gravitational lensing part. I would make it absolutely clear for you. Okay, I think the second part of the light, it's a bit off. I'll just correct that. Right. There you go. So imagine that the light, it finally comes over to the Earth and it hits the Earth in here and in here, some points here and here, right? And this is our little Earth, and the humans here, we have caught a bit of light. Now, there are actually two things which can happen from this point on. Two case studies, you may say, two scenarios, actually. That would be a better word to discuss as to what we are going to do. Now, imagine that when the light from this quasar, it came and hit the Earth. Imagine if we would measure it through a detector. Just write it out here for you. It's a very interesting concept, really. Right. So imagine if we got it through a detector. And when we get it through a detector, we get a pattern like this. Just a very simple pattern which we would obtain through a detector. What this would basically mean, for if you do not know, it basically means that the light which we have gotten is in the form of a particle, right? Now, this would be just case study number one, scenario one, which we could do. To move on to the second scenario, we need to understand another thing, which is this, an interferometer. Let me just take out the pen. Yeah, here we go. It is an interferometer. Basically, what an interferometer is a device which takes up two beams of light. It gives them out in a straight line, and it basically measures all the notations and all the things we require it to measure from light. So basically, interferometer is just a device. It would take out two beams of light, and in the end, it would send them out in a straight path, which would be like really close to one another. And it can do what all we ask it to do. It can give us some certain data, and we humans from that data do our measurements and all. Now, if the interferometer, if this device would detect light in a totally different manner. It would be in form of this, which is a particle, and a better perhaps drawing is given out here in the diagram which I chose for you. Should be the best to explain this topic. So this would be given out. The pattern like would be like this, and we would see that the light would be measured as a wave pattern. Now imagine that these were two totally like same cases, actually not same. Imagine that all the conditions were the same, but just like one set of humans, we got it through a detector, we got it as a particle. Now through a second one, we got this interferometer. Through this interferometer, we got it as a wave pattern. Now you may wonder as to like the light which had come out. Light had come out in the form of light. However, the devices which we used to measure and to see this light, they gave off two totally different things. One was a particle and the other was a wave. So what does this really mean? Is the light which would have emerged from this quasar, is it some particle or is it a wave? Now the question of light being a particle or a wave is a separate debate in itself. However, the thing comes here: does the future really influence the past? Basically, for the light, when it got out of this quasar, for it this would be the past for it, right? It would be from where it started, and when it hit the earth, for that it would be the future, and for the humans it would be vice versa, right? So So basically, after I'll remember that. So basically, after all the research which I did, we got up with this. The particle, the quanta particle, which was basically of the light. Because when we say a particle, I don't ultimately jump to the conclusion that the light which we received was in the form of a particle, and therefore case one was. I'm not saying that. It's just basically the light, the quantity, the quanta of light. It was made up of a wave of potential, and I'll be explaining this in the second point. It would become a lot more clear to you. Therefore, basically what happens is the light, it comes out in the form of a wave, right? And the quanta of light, it has a particular wave function and a wave of potential. So what happens is nothing was predetermined for light. For light, then it never like came out in a form of either a particle, nor did it come out in the form of a wave. It was only dependent upon how we used to measure it. The particle, the detector which used gave it out in the form of a particle here, but the interferometer, it gave out in the form of a wave. So basically, it is neither a wave nor is it a particle. It's made out just out of a wave of potential. Let me highlight this. This is the most important thing for you. So it is just a wave of potential, and as such, the potential, it would collapse into a definite state when it would be observed by some contraption or some machine, right? So if I would observe it through a detector, I would get a particle. However, when I would do the same for an interferometer, I would get a wave. Now coming back to our question, let's totally settle this question. Our question asked from us, does the future influence the past? Now, the ultimate answer to this question is like, obviously, first of all, we do not have that such a very specific answer for that. However, for this case study, we can say that the method, the frame of reference of the future, when I say the frame of reference, I don't, I mean it in a sense like the frame through the reference point through which we would wish to observe our given thing. The frame of reference for the future, that would be the thing which would determine as to how our received quantity acts as, either as a particle or as a wave. That settles our first thing, which would be it should be this thing, this entire contraption. Now, one thing before we end this part of this presentation is that our predetermined, as we know that it was not predetermined, it was only us by us humans, which either gave it out as a wave or a series of either a wave or a particle, right? And this is why the topic falls as a delayed choice, because this thing, it happened like billions of years back. However, it was only due to our delayed choice, our delayed method to perceive as to what this would be, either particle or wave. That was how this entire thing got its name, and it is commonly also referred to as a quantum eraser, which is a very interesting thing. Anyways, now let's come to the second part of my presentation, and it deals with gravitational lensing. And as I promised, I would now explain it to you. We saw that the light which would pass over, it came over in this form, right? It did not directly take a straight line path and come over. It rather had to bend. This is a very simple concept and quite a fun concept too, which was explained to us by Einstein. He gave out he merged space and time with one another, and basically what happened was objects which would possess a certain mass, they would start to bend the space-time, and that is the case for gravity. Let me show you the slide, which I mean. Yeah. I'll trim this out as well. Right. Okay, let's start from here in 3, 2. Right, 3, 2, 1. I'll trim this out. This is for myself, basically. Anyways, now the big objects, they would bend space-time. And for a galaxy, do you think it would be a small object? No, it would be a really large object. It would have a lot of mass, right? And it would bend space-time in such a way that for a very small particle, or for some very small thing like light would either have to take a path through here to go around to this, right? Like here, and would have to go. And this is actually how Einstein explained the concept of planets rotating with one another in orbit. And it's quite interesting. And also, either light could go down these two paths, or they could go around here and go here to where it wanted to go originally, right? So therefore, that's the entire concept of gravitational lensing. It happens when an object big enough to distort space-time. In fact, every object possessing a certain mass distorts space-time to an extent. You and I, we are also distorting space-time. But an object big enough which could distort like space-time to such an extent that it would cause such a huge depression in space-time that the objects around it would have to come with the paths which through that depression. And that is the entire concept of gravitational lensing. I hope you enjoyed the presentation. Moreover, I hope that you learned something new and liked the entire subject of quantum mechanics. If you do, then thanks and bye-bye.